Hello. In the previous lecture, we talked about integral domains and fields, and we showed that every field is an integral domain. We also discussed that the converse is not necessarily correct. For instance, when we look at the ring of integers, then it's an integral domain, but it's not a field. Though for the finite rings, we also showed that every finite integral domain is a field, but in general, an integral domain is not a field. Now, next, what we want to do, we want to construct a field that contains a copy of a given integral domain. The whole process is kind of like having rational numbers compared to integers. So having the integers, we can construct rational numbers. We want to do the same kind of process in order to construct the smallest field that contains a copy of a given integral domain. So let's look at rational numbers closer and try to mimic how we can construct rational numbers and create the field of fractions of a given integral domain. Every rational number is of the form, every fraction is of the form a over b, where a and b are, so we call a the numerator, b the denominator. Both of them are elements of this of z in this case, but in general they will be elements of our integral domain, and the denominator should be non-zero. So in a sense, every rational number is given by a pair of numbers, one of them arbitrary, the other one non-zero. So we can think about that the first entry, the first component of this pair of numbers is the numerator, and the other one is the denominator. But the subtlety is that two distinct pair of elements can give us the same fraction, can give us the same quotient. Now, that's the subtlety. This means what we are doing, we are putting a kind of equivalency between these pair of elements. We are saying that for us, two of them should behave the same way. 2, 1 should be the same as 4, 2. 0, 1 should be the same as 0, 2. Okay, so let's make it precise. What is this equivalence relation that I'm talking about? So again, we are seeking for this kind of property that a over b should be the same as c over d when a times d is the same as b times c. So if I have this equality, then we believe that we are getting the same fractions. So we take this computation from rational numbers and integers, and we try to extend it. We create field of fractions for an arbitrary integral domain. So suppose D is an arbitrary integral domain. So D is a given integral domain. It can be Z or an arbitrary integral domain that we don't know what it is. Then I pick two pair of elements. The first component can be anything inside this integral domain, and the second component consists of only non-zero entries, non-zero elements. Now, we say these two pairs are equivalent, and we define this equivalence relation for them. We say they are equivalent. We write like this. We say they are in this relation. If A times D, if the numerator of the first one times the denominator of the second one is the same as B times C, the numerator of the second one times the denominator of the first one. So I'm referring to the first component as the numerator and the second component as the denominator. Okay, the first thing that I have to show is that this relation is in fact an equivalence relation. But what does that mean? An equivalence relation, let's recall that a relation is called an equivalence relation if it has the following properties. Every element is equivalent to itself. We call this reflexive property. If an element is equivalent to another one, If x is equivalent to y, then y should be equivalent to x. We call this the symmetric property. And if x is equivalent to y and y is equivalent to z, then x should be equivalent to z. We call this the transitive property. Okay, so each one of them is actually easy to show. The first one is simply saying that, okay, so if I follow the definition of the relation that you said, I have to multiply the numerator of the first one by the denominator of the second one, and the denominator of the first one by the numerator of the second one, and I do get this equality, and therefore these two pairs are equivalent. Now, if A1B1 is equivalent to A2B2, that means that I have this equality. So these are the same. And from here, I have to be able to switch, but that's easy because in equality, I can switch. So it is clear that this is the same as this one, and I have this implication. So these two were easier than the third one. So let's go through the proof of the third one, which is a bit harder. And there is where actually we are using the fact that D is an integral domain. So far, I have not used the fact that D is an integral domain, and these computations were true for any commutative ring. But here is where I'm going to use the fact that I have cancellation law in D. Okay, let's go through the proof. Knowing that A1B1 is equivalent to A2B2 is the same as saying that A1 times B2 is the same as A2 times B1. Okay, knowing that A2B2 is equivalent to A3B3 is the same as saying the numerator of the first one, which is A sub 2, times the denominator of the second one, which is B sub 3, is the same as the numerator of the second one, which is A sub 3, times the denominator of the first one, which is B sub 2. Okay, so I have these equalities. I want to get to A1 times B3 equal to B1 times A3. This is my goal. I want to reach this kind of equality. So this means I need to have an equality, and one side I need to have A1 and B3. So if I look at the equations that I have over here, on the left-hand side, I do have A1. That's good. That's one of the players that I care about. But I also need B3 that I don't have here. So what can I do? I can multiply both sides by B sub 3. So that's what I do and hope for the best. So let's see where we get to. So here, when I multiply both sides by B sub 3, I end up getting A sub 1, B sub 2, B sub 3, and that's equal to A sub 2, B1, B sub 3. Okay. Now, again, let's go back to our targeted equality. So our targeted equality, on one hand, we had A1, B3, on the other hand, we had B1, A3. Now, looking at the second equation, I do have A3 over here, but I do not have B1. So I'm going to multiply both sides by B sub 1. And I end up getting that it is A sub 2, B sub 3 is the same as A sub 3, B sub 2. Now, I get two sets of equalities. I look at them and I realize that the right-hand side of the first one is the same as the left-hand side of the second one. So these are the same. So that means the left-hand side of the first one, which means this, is the same as the right-hand side of the second one. So if I write it down, I wrote it here, I get A1, B2, B3 is the same as A3, B2, B1. Notice now B sub 2 is a denominator, so it's non-zero. And D is an integral domain, it's commutative. And we have cancellation law. So what I can do, I can cancel out B sub 2 from both sides. By canceling that, I end up getting a sub 1 b sub 3 is a sub 3 b sub 1, and that's exactly what I was looking for. So overall, we end up showing that this relation that we are introducing is indeed an equivalence relation, and therefore I can talk about the equivalency class compared to this, with respect to this relation. The equivalency class of the pair A comma B is denoted by A over B, and we call it the fraction of A over B. This is exactly, it behaves the same way as we expect, meaning when I multiply A and B by the same thing, by the same non-zero element, we end up getting the same fraction because of the way we define the relation between the pairs. The set of all the fractions where the numerator is arbitrary, the denominator is non-zero, is denoted by, we will denote it by Q parentheses D, and we call it the field of fractions. I have to justify the name, and we will do it next. But first, for now, let me write down what we call this guy. We call it the field of fractions. The field of fractions of D. So it's the set of all equivalence classes A comma B's that we denote by A over B. Okay, so I want to make this Q parentheses D into a field. I want to say that it is a field. Okay, this means I need to define two binary operators and first discuss why it's a ring with respect to these binary operators. So we will borrow our intuition from rational numbers. So when I give you two fractions, how do I define the addition? We take a common denominator, and that way we can add them. So A over B plus C over D is similar to rational numbers. We define it to be A times D, the numerator of the first one times the denominator of the second one, plus C times B, or B plus B times C, because it's commutative, it doesn't matter. I can choose whatever ordering I want, divided by B over D. So I'm defining summation of two fractions to be this new fraction. And similarly, we can define multiplication of two fractions to be multiplying the numerators and then multiplying the denominators. Now, there is a warning. What is the warning? The warning is that we have to show these operations are actually well defined. What do I mean by that? You see, the way that I'm defining these operations depend on the choice of the numerators and denominators, even though the fractions can be represented by different numerators and denominators. So what we need to show is that no matter what choice you pick for representing this fraction, you end up getting the same result at the end. So again, let's make it precise. If I manage to write down the same fraction a1 over b1 by two other elements, a sub 2 and b sub 2, and if I manage to write down the fraction c1 over d1 by some other pair of elements of the integral domain, c sub 2 and d sub 2, then I have to say that I end up getting the same addition. The formula that we have for addition ends up giving us the same fraction. So you see, if I use the representatives a1 over b1 for this fraction and representative c1 over d1 for the second fraction, the formula that we have for summation says that summation should be a1 d1 plus b1 c1 over b1 d1. But if I use the second representatives for the same fraction, I end up getting that it is a2 d2 plus b2 c2 over b2 d2. A priori, it's not clear why I'm getting the same fractions. So that's what I need to show. I need to show that these two fractions are the same. The same statement holds for multiplication. So we need to say why a1 c1 over b1 d1 is the same as a2 c2 over b2 d2. So again, if we are choosing representatives and arguing certain property based on those representatives, we have to argue that it doesn't matter what representative you pick. No matter what representative you pick, we have to get the same result. Okay, so again, A over B is the equivalence class of the pair of elements A over B, and this A comma B, and if I choose another representative from the same equivalence class, I have to get the same result. The second equality is actually rather easier than the first one, so I will check only the first one, why the addition is well defined, multiplication is a bit easier. So let's start checking why I have this property that A1 D1 plus B1 C1 over B1 D1. Why is this fraction the same as this one? But remember, two fractions are the same precisely when the numerator of the first one times the denominator of the second one is the same as the numerator of the second one times the denominator of the first one. So that means I need to check this equality. The numerator of the first one times the denominator of the second one. Why is this one the same as the numerator of the second one times the denominator of the first one? Let's distribute. Of course, the first equality holds if and only if after distribution the equality holds. So when I distribute, I get that A1 D1 times B2 D2. Why is this one the same as B1? Okay, so A1 D1, B1 B2 plus B1 C1 times B2 D2. Why is this the same as A2 D2 times B1 D1 and B2 C2 times B1? Okay, so I need to check this equality. But let's go back to what we have. This is our target. We want to reach to this equality. But let's go back to our assumption. What do we know about A sub i's and B sub i's? What do we know about C sub i's and D sub i's? So the assumption was that A1 over B1 and A2 over B2, both of them are the same fractions. They are representing the same fraction. What does that mean? This means that the numerator of the first one, which is A1, times the denominator of the second one, which is B2, is the same as the A2 times B1. So I have this equality, and similarly, I do know that C1 D2 is the same as C2 A1. Okay, so now I know these, but how can they help me? Let's go back and look at the target equality. In the target equality, I have, okay, so I have A1 B2, and there it is. This is A1 B2 that I have over here. And I do know that it's the same as A2 B1. And here it is. This is A2 B1. And when I compare these two terms, I see that this term is indeed the same as this one. They are equal because they are essentially this equality multiplied by D1, D2. So which equality? This equality times D1, D2 gives us the one that I use the green curly lines and box them. Now, similarly, if I use, let's use this color, if I look at C1 D2, here it is C1 D2, and that's the same as C2 D1, and here it is C2 D1. And when I multiply this by B1, B2, I end up getting these terms. So this means that the second terms are also equal, and we get the desired equality. So overall, what we showed is that if I pick two different representatives of the same fraction, the fraction that we get as the summation of those are actually the same. And therefore, addition is well defined. Similarly, you can check why multiplication is defined. So far, we defined two binary operations on the field of fractions. But next, I want to discuss that indeed we are getting a ring. Okay, so in order to show that we are getting a ring, we have to check many things. For instance, why do I have a 0? And again, similar to rational numbers, we know a 0 should be 0 in the numerator and denominator arbitrarily. So let's actually check it for denominator 1. So 0 over 1 plus a over b, when I add them, I end up getting, by the way that we defined addition, the numerator of the first one times the denominator of the second one gives me this, and then denominator of the first one times the numerator of the second one gives me this, and then at the end I have to multiply the denominators. 0 times anything is 0, 1 times a is a, so I end up getting same fraction, a over b. So this shows that this is the neutral element, because when I added to this guy, I ended up getting the same fraction. So that means that 0 over 1 is the 0 of this ring. It's also useful to write this down, that notice that 0 over 1 is equal to 0 over b for every b, because 0 times b is 0, and it is the same as 0 times 1. So they are equal, and therefore these fractions are the same. So this means 0 over any denominator represents the 0 of these fractions, the set of fractions. Now, how about 1? Now, 1 over 1 times a over b, by definition, is 1 times a over 1 times b, which means it is a over b. So this means, again, when I multiply it by a over b, I end up getting a over b, and therefore 1 over 1 is the identity of this ring. And it's also useful to notice that 1 over 1 is the same as a over a, as long as a is not 0. And therefore, all of these represent the same identity. These are compatible with your intuition from rational numbers. You see that all of them can go on, so all of them work for field of fractions of an arbitrary integral domain. I do not check all the properties of being a ring. Namely, I do not check why addition is associative, why we have negatives. Negatives, again, similar to rational numbers. We just take the negation of the numerator. Why we have distribution property. All of them are actually rather easy, and I leave them to you to check them. But let's see why it is actually a field. What does that mean? This means I have to take a non-zero fraction, and I have to show that it's a unit. So I pick a non-zero fraction. So let's call it a over b. And it's non-zero, which means it's not the same as the fraction 0 over 1. Now, because a over b is not the same as 0 over 1, this means what? This means that when I multiply a by 0, it's not the same as multiplying b by 0, but b times 0 is 0, and a times 1 is a. So this means that we do know the numerator is not 0. Therefore, I can talk about the fraction b over a. You see, whenever I want to talk about a fraction, the denominator should not be 0. So that's my argument, that the numerator a is not 0. So I can talk about b over a, and b over a is an element of this field of fractions. Okay, so I'm still calling it field of fractions, but I'm trying to finish off the proof that why it is a field. So now my claim is that b over a is indeed the inverse of a over b. Let's multiply them. So a over b times B over A. By definition, and commutativity of D is the same as AB over AB. But then, as we discussed, and we have it over here, any number over any element over itself is the same as 1 over 1, and therefore we get that this product is the identity of the ring Q parentheses D, and therefore A over B is a unit because I managed to multiply it by something else and end up getting 1, or identity of this ring. So that overall implies that I end up getting a field. So the set of fractions coming from an integral domain D forms a field in a natural way. And we call this the field of fractions of D. Now, next I want to say that first of all, D can be embedded inside this field. And second, it is the smallest field that contains a copy of D. Let's start with embedding D into this field. And we borrow again our intuition from integers and rational numbers. How do we view an integer as a fraction? So we pick this integer 5, and then we think about it as 5 over 1, and think about it that way we can view it as a fraction. We do the same for an arbitrary integral domain. So when I give you an integral domain D, then we can define this function I from D to the field of fractions Q parentheses D that sends A to a fraction with numerator A and denominator 1. Now my claim is that it's an injective ring homomorphism. An injective ring homomorphism is called a ring embedding. So when I say that I can embed a ring into another one, so when we say we can embed a ring into another one, a ring R, embedding a ring R into another ring S. So this means, let me continue here. That we find an injective one-to-one ring homomorphism from R to S. So if I have such a thing, then we say I can embed R into S. I can have a copy of R inside S. Okay, so let's check why I is indeed an injective ring homomorphism. So that means I have to check why it preserves addition, why it preserves multiplication, and why it is injective. Okay, let's start with addition. So I of A plus I of B is A over 1 plus B over 1. By definition of adding two fractions is precisely A times the denominator. It's over here, and it is B times the denominator, which is over here, and the denominator times the denominator. So all together, we end up getting that this is precisely A plus B over 1. That's I of I plus B. Now, I of A times I of B is, again, when you write it down, you see that it is I of AB. So it's a ring homomorphism. Now, let's see why it's injective. So why is it injective? Injectivity means what? It means if I look at I of A and I know that it is the same as I of A prime, why do I have that A is A prime? So what does that mean? I of A is A over 1 and I of A prime is A prime over 1. Knowing that these fractions are the same means the numerator times the denominator, which is A times 1, is the same as the denominator times the numerator, which is 1 times A prime, and we get the desired equality. So it's an injective ring homomorphism. That means we end up finding a copy of D inside these fractions. Next, I want to say that this field is indeed the smallest field which has a copy of D in it. I have to make sense of this statement. What do I mean that it is the smallest? These are not numbers, so there are no inequalities between them. And what do I mean by copy? The copy we have already discussed. Having a copy should mean that I should have an injective ring homomorphism from D to this field, whatever that field is. So this brings us to what we call the universal property of field of fractions. So it's an important, maybe this is the most important property of field of fractions. And I do not expect you to know all the details of the definition of field of fractions, but what I do expect you to know is this property. You have to know what is the universal property of field of fractions, and you have to know how to use this universal property. Okay, what is it? I give you an integral domain. I give you a field that has a copy of D in it. What does that mean? So I'm giving you an integral domain, and I'm giving you this field that has a copy of integral domain, which means there is an injective ring homomorphism, from D to F. That means it has a copy of this integral domain inside F. Now, in that case, so if I have a copy of D inside F, then I want to extend this copy and get a copy of the field of fractions inside F. So that way, I can say that the field of fractions is the smallest one, the smallest field that has a copy of D, because any other field that has a copy of D in it has a copy of the field of fractions as well. So that's, in that sense, we say the field of fractions is the smallest field that contains a copy of an integral domain. Okay, now what is that embedding? We give it, actually, we give a concrete ring homomorphism, injective ring homomorphism from the field of fractions of D into F. What is that? It is in the natural way. So F tilde from the field of fractions to F, if there is such a thing, then F tilde of A over B, if it's supposed to be compatible with what we have for the integral domain D, then it should be F of the numerator times inverse of F of the denominator. Notice that we have that here, notice that A over B is A over 1 times 1 over B. And that is, you remember, this is I of A times I of B inverse. So the copy of D inside Q of D, that's given by I. So any element of the field of fractions is one element inside this copy times inverse of the other one. And if my F tilde is supposed to be compatible with F that we have, that means I have to define it like this: F of the numerator times inverse of the F of the denominator. Okay, so that's how we are defining it. And then the claim is that this function is actually well defined, and it is injective, and it's a ring homomorphism. So that means we find a copy of the field of fractions inside this field capital F. And we have this very nice, I mean, when I say compatible with the function f, it means this diagram over here. So let's try to understand this diagram a bit better. So I mean this diagram over here. So when you think about it, it means when I go from D to the field of fractions via I, or when I go from D to the field capital F via this embedding small f, then I am finding this embedding of the field of fractions from Q parentheses D to capital F that we denoted by F tilde, and this embedding is compatible with the embedding of D, which means what? Which means if I start from an element, A inside the integral domain and go via I, that means I end up getting to the field of, to the fraction A over 1, or if I go via F and I end up getting F of A, it's the same as going up, going to the fraction A over 1, and then using this function F tilde in order to go from the fraction A over 1 to the field F. I have to say why, because the way that we defined it, F tilde of A over 1 is F of A times F of A, F of 1 inverse. So I need to say why F of 1 is in fact 1. So I need to justify this equality. But so these are the things I have to show. I have to show why F tilde is well defined. I have to show why it's injective. I have to show why it's a ring homomorphism. And at the end, I need to show why F of 1 is 1. And therefore, I get the compatibility of this injection of the field of fractions and the injection given to us of D inside F. So again, let me repeat. If I have a copy of an integral domain inside a field, then we can extend this and get a copy of the field of fractions of D inside the same field. So that's the content of universal property of field of fractions. Okay, let's go through the proof. Let's start with why it is well defined. Again, what does that mean? It means when I give you the same fraction, but with two different representation of the same fraction. So if I give you two different representative of the same fraction, if I give you A1 and B1, A2 and B2, so that A1 over B1 is the same as A2 over B2, then I need to show why F tilde gives me the same element of the field capital F via this rule that we have. So we need to show, again, we need to show why F tilde of this guy is the same as F tilde of the second one. After all, they are the same fractions, and F tilde is supposed to be a function on fractions. So I need to have the same value inside the field capital F. But the way that we define them, the way that we define them in what's over here, it depends on the choice of the numerator and denominator a priori. And I have to say that it is actually independent of that choice. Okay, so let's start again by knowing that when I tell you these two fractions are equal, then that's the same as saying that numerator times the denominator, A1 times B2, is the same as A2 times B1. Knowing this, I can apply the ring homomorphism F to both sides. And I get that F of A1 B2 is the same as F of A2 B1. But F is a ring homomorphism. That means it's F of the first one times F of the second one. And that's the same as F of the second one, F of A2 times F of B1. Now notice that B sub i's are denominators, so they are non-zero. F is injective. That's the crucial part that we are using injectivity again. F is injective. If F is not injective, this process doesn't work. F is injective, and therefore F of Bi cannot be 0. Now, capital F is a field, and I'm giving you a non-zero element of this, so F of Bi inverse actually exists. It's an element of the ring, of the field capital F. Now that it does exist, I can multiply both sides of this by inverse of F of B2 and by inverse of F of B1, and end up getting this equality, that's exactly what we was that's exactly what we were looking for. That's exactly showing that f tilde is well defined. I'm getting the desired equality. It does not depend on the choice of representatives. Now, the fact that f tilde is a ring homomorphism is easy. You can check addition and multiplication. Why it preserves addition and multiplication, I leave it to you as an exercise. Let's see why it is injective. I'm not saying that this is harder than the other ones, but I want to recall a fact from group theory. Yeah, I think it's a good place to recall this. We are going to use it again and again later on. So let's recall this fact. What is the fact? It says that a group homomorphism is injective. A group homomorphism is injective if and only if its kernel is trivial. But what does trivial mean? It means that the only element that's in the kernel is the neutral element. So in the additive setting, is the same as saying that the only element that's in the kernel is 0. So this means we have to show that if f tilde of some fraction is 0, then that's the 0 fraction. If we show this, then we are getting injectivity of f tilde. So again, in order to show that f tilde is injective, we need to show that if f tilde of a fraction is 0, then that fraction is 0. Okay, so let's follow the definition of f tilde. F tilde of a over b, by definition, is f of the numerator times inverse of f of the denominator, and that's supposed to be 0. I can multiply both sides by f of b, and I get that f of a is 0. But f is injective, therefore the only element in the kernel of f is 0. And knowing that f of a is 0 means a is in the kernel of f, therefore a is 0. Okay, so that's knowing that a is 0, that's the same as saying that the fraction a over b is the same as the 0 over b, because a is 0, and 0 over b is the same as 0 over 1. So we just showed that the only element in the kernel of f tilde is the 0 element, and therefore f tilde is injective. Now the last thing that I want to show is about the diagram that I showed you, and why this f tilde is compatible with f. And as I've discussed, it's enough to show why f of 1 is 1. Let's see what is f of 1. The critical equation in most of these type of things, you had it in your one of the problems in the discussion and problem session as well, that we discussed f of 1 times f of 1 is, because f is a ring homomorphism, is definitely f of 1 squared, but 1 squared is 1. So f of 1 times f of 1 is f of 1. This is a kind of useful equality that can help us to characterize all possible ring homomorphisms from a given unital ring to another one. But in the case where my target is a field, and f is injective, we do know that f of 1 is not 0, and capital F is a field, and in particular it's an integral domain. I can cancel out f of 1. So by canceling f of 1, I end up deducing that f of 1 is actually 1. And that's exactly what we wanted to show in this diagram, that where we wanted to discuss why the f tilde that we have is compatible with the initial injection, initial embedding of the ring D inside F. Okay, so overall we proved this crucial property of field of fractions that we call universal property of field of fractions. But let's see how we can actually use it. How can we use universal property of field of fractions? Okay, let's try to use that. Let's see an example. So let's look at the subring of complex numbers that's given by elements of the form a plus bi, where a and b, both of them are integers, and another subring of complex numbers, q bracket I, where the elements are of the form a plus bi, where a and b, both of them are rational numbers. Now my claim is that the field of fractions of z bracket I is isomorphic to the ring q bracket I. You've seen in your, again, you've seen this kind of questions before. Why these things you've seen before? I'm assuming that you remember, and that these, both of them are actually subrings. So both of them are subrings of complex numbers. You know how to prove that. Okay, now in this question, we want to focus on why the field of fractions of z bracket I is isomorphic to q bracket I. I will give you a general method of showing that field of fractions of a given integral domain is isomorphic to another ring F. So the steps are of the following forms. The following 4 steps you can use in order to show that the field of fractions of D is isomorphic to the ring F. The first thing is to show that in fact this F that's given to us is indeed a field. So the first thing that we do is to show F is a field. The next thing that we do is to find an injective ring homomorphism from D to this field F. Usually this step is quite natural, and we have a very natural embedding of this integral domain into another one. So, but that should be mentioned. We have to find an injective ring homomorphism from the given integral domain to this given ring F. Then the third step comes for free out of the universal property of field of fractions. Using the universal property of field of fractions, you have to deduce that there is an injective ring homomorphism F tilde from the field of fractions of D into F. That's given by this equality, that F tilde of the fraction A over B is the same as F of the numerator times inverse of F of the denominator. Okay, so the third part we just get for free out of the universal property of field of fractions. Then finish it off by showing that every element of the ring capital F is indeed of the form F of A times inverse of F of B for some A and B. So the fourth part tells us that F tilde is surjective. So this tells me that it is surjective. We have already the way that we got F tilde is that it's an injective ring homomorphism. So overall, we deduce that F tilde is a bijective ring homomorphism, and therefore it's an isomorphism. So overall, we get that F tilde is an isomorphism from the field of fractions of D into F. And that finishes our proof. So these are the 4 general steps in order to show that field of fractions of an integral domain is a field F. Let's go through this for Z bracket I, and we finish today's lecture by this example. Okay, so okay, so actually I am going to resume this. We finish this part in the next lecture. Let's stop for now.